Hello guys, today we start to study chapter 8, Nucleus. This chapter contains 16 sections divided into 4 parts. We will learn about atom and nucleus, radioactivity, nuclear energy including fission and fusion, and elementary particles. Thomson proposed the first atomic model that describes an atom as a positively charged lump of material with electrons embedded in it. But the Thomson model conflicts with the Rutherford experiment of alpha particle scattering. The result of Rutherford experiment indicates atom to be largely empty, positive charges to be concentrated at the center as a nucleus, and the negative charges to be surrounding the nucleus at a distance. This constructs the Rutherford model of atom. A nucleus is made of two types of particles, protons and neutrons. A proton has charge positive E and mass 1836 times that of electron. A neutron is a neutral particle and has mass 1839 times that of electron. For different atoms, their nuclei have different numbers of protons and neutrons. The atomic number usually denoted as Z is the number of protons in the nucleus. The mass number usually denoted as A is the number of protons and neutrons in the nucleus. For some examples, the atomic number of hydrogen is 1. The mass number of helium is 4, and so on. A nucleus is usually represented based on its chemical symbol X, atomic number Z, and mass number A. XZA. For some examples, hydrogen is represented by H11, helium is represented as He24, and so on. Atoms or nucleus of the same element but with different number of neutrons are called isotopes. For some examples, deuterium and tritium are two isotopes of hydrogen. A nucleus with too many neutrons is unstable, so that it emits particles or high-frequency electromagnetic waves. This phenomenon is called radioactive decay. There are 5 types of radioactive decays. Alpha decay as the emission of alpha particles, which are the helionuclei. Beta decay as the emission of electrons. Gamma decay as the emission of gamma rays. Positron emission as the emission of positive electrons. And the electron captures as the absorption of electrons. Gamma rays have the best ability to penetrate, while alpha particles have the least ability to penetrate. Different radionuclides radiate in different timescales. The time needed for half of radionuclides to decay in an original sample is called the half-life. For example, given the half-life of a potassium isotope to be 1.2 billion years, find how many years does it need for 7/8 of the original potassium to be decayed. Since 1/8 of the original potassium is left, 3 half-life period is needed, i.e. 3 times 1.2 equal 3.6 billion years needed for 7/8 of the original potassium to be decayed. All ionizing radiation is harmful to living tissues. Radiation level is measured using the SI unit sievert, or shortened by SV, with 1 SV equal to 1 joule of X-ray or gamma rays absorbed by 1 kilogram body tissues. Sources of radiation include random gas, radionuclides in rock, soil and body, nuclear reactors, hospital hospital medical X-ray machines, and cosmic rays. The unit kilogram and joule are too big for the mass and energy of atomic particles. For convenience in atomic or nuclear physics, we usually define a new mass unit called atomic mass unit U, with 1 U equal to 1.66 times 10 to the negative 27 kilogram. With the atomic mass unit, the mass of proton is equal to 1.0078 U, and the mass of neutron is 1.0087 U. The unit for energy of particles is electron volt, shortened by eV, with 1 eV equal to 1.6 times 10 to the negative 19 joule. It is the work done by moving an electron across 1 volt electric potential difference. 1 mega electron volt, 1 MeV, is equal to 10 to 6 electron volt. From Einstein's mass-energy relation, E equal mass mc squared, we have 1 U mass to be equivalent to 931 mega electron volt energy. The energy needed to bind nucleons together tightly to form a nucleus is called binding energy. It is equivalent to the energy of the missing mass, which can be calculated based on the total mass of individual nucleons subtracted by the nucleus mass. Dividing the binding energy by the mass number, we have the binding energy per nucleon for the nucleus. For example, find the binding energy for helium-4, whose mass is 4.0026 U. From the binding energy formula, substituting the numbers into the formula, i.e. 2 for the atomic number Z, 4 for the mass number A, 1.0078 for the proton mass MP, 1.0087 for the neutron mass Mn, and 4.0026 for the helium-4 mass M-helium-4, we have the missing mass to be 0.03 U. Multiplying 931 to 0.03, we have the binding energy to be 28 mega electron volt. Dividing it by the mass number 4, we have the binding energy per nucleon for helium-4 to be equal to 7 mega electron volt per nucleon. There are two processes to generate nuclear energy, fission and fusion. Fission refers to splitting of a heavier nucleus into two medium-sized ones. For example, the fission of uranium-235. With many radionuclides, a chain reaction can occur. An uncontrolled chain reaction of fission leads to explosion and makes an atomic bomb. A nuclear reactor is a nuclear power plant that transforms nuclear energy to electricity. The fission in a reactor must be controlled, usually by slowing down or absorbing the neutrons from the fission. A nuclear reactor first converts nuclear energy from fission to heat, then removes the heat by coolant that heats water into steam to drive the turbine and generate electricity. As we talked in Chapter 4, Section 8, there are 435 reactors made in 30 countries in the world, with 3 significant disasters occurred. Accidents. We don't repeat here. Except for uranium-235, plutonium-239 obtained from non-fissionable uranium-238 after 2 beta decays can be also fissionable nuclei for reactors. As another process for nuclear energy, fusion refers to joining 2 light nuclei to give a single medium-sized one. For example, the fusion of 2 isotopes of hydrogen, deuterium and tritium that can release 17.6 MeV energy. Hydrogen bomb from fusion has been very successful for many years, but a fusion reactor has not yet been made because it requires extremely high temperature, over 10 to 8 Kelvin, high concentration, and a long confinement time. At present, scientists try to heat plasma by current, wave, and so on, to confine the hard plasma by magnetic field, or to compress by laser beams to ignite the fusion, but still not successful. Particles that cannot be separated into others are called elementary particles, such as electron, neutron, proton, muon, pi, neutrino, and so on. There are over 300 elementary particles discovered in nature or made in the lab. Each particle has a corresponding antiparticle that has the same mass but opposite sign of charge. For example, positron is an antiparticle of electron. When a particle combines with its antiparticle, annihilation occurs and produces 2 gamma rays. For example, annihilation of positron and electron emits 2 gamma rays. The inverse of annihilation is called pair production. That refers to that a particle and its antiparticle are materialized from energy or gamma rays. As we mentioned in Chapter 1, there are 4 fundamental interactions found in the nature. There are strong interaction, weak interaction, electromagnetic interaction, and gravitational interaction. The strong force holds protons and neutrons tightly to form nuclei. It is short-range interaction, about 10 to -15 meters. Weak interaction affects all particles in an even shorter range of interaction and 10 trillion times weaker than strong force. As we have talked in Chapter 6, electromagnetic interaction governed by the Coulomb's law is the interaction between electric charges. It is a long-range interaction. Gravitational interaction governed by Newton's gravitational law is the interaction between masses. It is also a long-range interaction. The ultimate goal in physics is to unify all interaction in a single theory. So far, successfully developed unification theory include the QED for the unification between weak and electromagnetic fields, the QCD for the unification among strong, weak, and electromagnetic fields, and 5D gravity for unification between gravitational and electromagnetic fields. All elementary particles can be categorized into 2 types based on their participation of strong interaction or not. Particles that do not participate in the strong interaction are called leptons, such as electrons, neutrinos, and so on. Particles that participate in the strong interaction are called hadrons, such as protons, neutrons, and so on. Hadrons are suggested to be composed of quarks, which have 6 types or flavors, named as up, down, charm, strange, bottom, and top, respectively. Quarks have fractional charge and cannot be pulled out from hadrons. In other words, quarks cannot exist independently. This is the end of this chapter. Thank you.